I haven't done quantum chemistry during the past years. So what I'm talking about here is mainly based on some stuff we did about 4 years ago together with my former master student Fabian Faulstich, who already is here, and together with Ursula Geza, and also with Simon Qual and his student Andre Laestadius from the University of Oslo, and he is connected to the Hilleras Center. And but recently, I would say it's 1 week ago, yeah, I was invited by Simon, and I just resumed this topic, and motivated by Simon's idea, I think we are looking forward to have a relatively new formulation. And what I feel already uncomfortable here is that in this conference, coupled cluster is considered as someone bad, old stuff, and expensive. Someone one wants to avoid, yeah. And I'm doing just the opposite around, yeah. I'm really want to talk about coupled cluster, and but it's already have in mind that in this respect we are interested in high precision, and we are restricted to still relatively small systems. Okay, so first thing is, at least the first motivation I come back is, so we are trying to solve the electronic Schrdinger equation by wave functions method, and so we want to find an approximate wave function which is parametrized in a nonlinear way. And I will look for two kinds of nonlinear parametrization. One kind is a famous coupled cluster parametrization, where we have this exponential function, this exponential parametrization. And in contrast to this is a nonlinear parametrization, where we are approximating the wave function inside a large, extremely large configuration space, full ZI space, but on a low-dimensional manifold. And this already is a manifold, or maybe it's an algebraic variety. And what I consider here is a manifold of what is called matrix product states, as a simple example of tree-based tensor network states. Yeah? And this has been introduced here. It's the main solution technique is known as DMRG, and I'm I'm happy that here my chairman here is already one of the experts in, or pioneers in this quantum chemistry stuff. What? Retired. Retired, yeah. Okay. So these are completely different parametrizations, yeah, and they cover only a small part in the configuration space, but hopefully this is an important part. But these parts are quite different. And I will talk about a combination of both approaches to improve the DMRG. So this was my motivation to improve the DMRG algorithm. But I will explain it here in the sequel just by improving at first the coupled cluster. And what we are using as improved coupled cluster methods are already, I would not say established, but they are already known method in multi-reference coupled cluster theory. Okay, so okay, and the idea is that we really want to compute effects which are beyond the capability of single reference coupled cluster. So usually people say strong correlation, but already can have in mind other things which I think is not so easily done with coupled cluster, single reference coupled cluster, namely excitation-excited solution, or a time-dependent coupled cluster. Yeah. So and the thing is, we want to base it on a DMRG approximation, but really it's a coupled cluster. This nonlinear parametrization, this provides important information about the electron-electron cusp and brings us into the possibility to at least make the basis set error relatively small. Okay, here's a second motivation, but I think I will skip it. Maybe I can discuss it a little bit later, why this, at least in an abstract sense, fall into the perspective of multiscale methods. So, and I acknowledge this was my starting point, or this was our starting point, is this paper. And I worked together with Ursula Gezer, who was one of the first developers in quantum chemistry, DMRG. Yeah? And he met this Prague group of people from coupled cluster. Yeah? And they had a quite exciting idea using what they called tailored multi-reference coupled cluster. And I was surprised at how easily it can be applied to DMRG. So let me explain coupled cluster in a few minutes. I already heard that there was a tutorial, and so I think you are a little bit familiar with coupled cluster. Yeah? So I start with the definition, textbook definition of annihilation and creation operators. By definition, how we define these operators? By its action onto Slater determinants. Yeah? So the Slater determinant is built as an antisymmetric product of orthogonal basis functions, and the annihilation operator, if we just order this way around Aj, it just annihilates the first determinant, though at the end you have a determinant of a smaller size, yeah? And a joint operator is a creation operator, and with this formulation, one can really reformulate the Schrdinger equation, or at least the full ZI Schrdinger equation, in the following form. So here we have a combination of annihilation and creation operators, and here this is a single particle operator, and this is a one electron integral, and here we have these two electron integrals and the two electron parts. Yeah? And you see that this representation is really depending on the basis entering the Slater determinants. Yeah? And see, as already these integrals are basis dependent. The definition of these operators here as operating on wave functions is then already basis dependent, but we will see later some contrary of this. Okay, and next to define the coupled cluster ansatz, we introduced excitation operators. And for example, the x1k is doing the following. It annihilates the first orbital from psi naught and replace it by the orbital phi k. Yeah? So like just a trainer in a sport, putting one person out and new person in. Yeah? And by this definition, we can already create higher excitations by just considering the product of this operator here. And the important thing is that we annihilate only a certain set of orbitals, namely the occupied orbitals. These are the orbitals inside the reference determinant. Usually it's a Hartree-Fock determinant. These are the only, and we create only unoccupied orbitals. That's a strict rule. Yeah? Because if we do this rule, then these operators here, they commute. Okay? And with a intermediate normalization, though, if the wave function is not orthogonal to the reference, then we can really write the full ZI wave function as a linear combination of here psi 0 plus and here excited Slater determinants. Yeah? Yeah? And this index mu is just the index for the corresponding Slater determinant. You see a little bit later. And this is a linear ansatz. So you see you have a linear parameterization of the wave function. Okay, and now I come to the complete active space stuff. And in this, we go a little bit further. So far, we have considered the set of occupied orbitals. These are the orbitals inside the reference determinant. Usually the reference determinant is a Hartree-Fock determinant. Yeah. So if we have n electrons, then we have here n orbitals, and the others, and then we add this set of orbitals. These are orthogonal basis functions by d additional ones, and we call this the active unoccupied orbitals. Yeah? And the d is a relatively small number. Yeah? And then additionally, so there, and this now is a set of orbitals we use to construct the complete active space. That's the active space we will do later full ZI calculations. And then we add further orbitals, namely the red ones here, and we call this external unoccupied, or shortly external orbitals. Yeah? And we go up to the size of the full basis set, capital K. Yeah? So usually capital K is supposed to be a large number, tending to infinity. Yeah? So maybe 100 or something like this. Yeah? Okay. So, and now here we have this excitation stuff, and in the picture, usually blue are the occupied and the active unoccupied ones, and the reds here are the external. Yeah? And maybe if you have further orbitals really going to infinity, one may call virtual, but I do not consider these orbitals here, only to say that if we have such a kind of ansatz, and we work in the full configuration space with these capital K ones, yeah, we get a full ZI solution up to a basis set error, which is behind here. Yeah? And it is clear if we are working on a smaller space with full ZI, then the basis set error is much larger. Yeah? Okay. So, and just for the motivation, I start with the intermediate normalization, which is typical for coupled cluster and quite helpful. So I have already explained this linear parametrization. Yeah? And now instead of this linear parametrization, you see that we add to the reference determinant a linear combination of excitation operators applied to psi0. Yeah? Exactly of this form. Please.
Yeah, the previous slide. So this IK, does it include like all the excitations? Like
so these I's, the IK and this are for the occupied one.
Calligraphy IK. Next line. Next line. In the next line, sorry, the same slide.
Here.
Alpha in, yeah, so BK equals to psi naught up with the alpha equals to IK.
Yeah, so this is the basis, is the full basis, so it's a full basis. Yeah, okay?
IK include all the
excitations. IK include all excitations from here to here. Yeah, okay?
From the CAS to the external.
Yeah, yeah. I will say this later. At first, these are all. Yeah? Okay. And first, I explain the coupled cluster ansatz, and then I show you the restricted one. Okay? Yeah. So in the coupled cluster ansatz, we define an excitation operator as linear combination of these excitations here, and mu is such an index, and defines the wave function as an exponential. The exponential of this operator applied to psi0. And this exponential can be computed quite easily because these operators here are commuting. Yeah, that's okay. And then it is clear. So if this is if psi is supposed to be the solution of the full ZI, and E is a full ZI for the full scheme, then Hamilton operator applied to psi is equal to E times psi. Yeah? And typically we are looking for ground state. Yeah? So it's a coupled cluster method is a golden standard for ground state calculation. Yeah? Okay. And now instead of this linearized, okay, and then we obtain the following set of equations, that these equations should hold for all excitations here we allow, so, and this is now a set of excitations, and it should already hold for the reference case. And you see that here, okay, that's nothing by plugging in this exponential ansatz. But there exists another formulation. This is now called the linked coupled cluster formulation, is that here we apply the Hamilton operator to the wave function, and now we apply the inverse of this exponential excitation operator again. Yeah? So this is a similarity transformed. It is no longer a Hermitian operator. Yeah? It is no longer symmetric. It is similarity transformed. It has the same eigenvalues. Yeah? Okay. And then it turns out that if we, and then the problem is the same as here. So we get a wave function, but now we have to, in order to get a set of equations for so many unknowns here as indices, we are projecting on a linear space. And the linear space is just the corresponding ZI space. So that's just the excitation of psi 0. I call it psi mu. Okay. And if I do this, if I apply this here again, then for all excited, so if I apply an excitation to the reference and testing this with this transformed operator applied to psi 0, then all these expressions are 0. Except if there is no excitation, and then I have the inner product with psi 0, and this is just the energy. Yeah? Okay? But forget the energy here. The point is that if now mu is in this A, then this is a nonlinear system. This is a nonlinear system for the unknown excitation amplitudes, coupled cluster amplitudes T mu. And the advantage of this is that this expression, so the exponential function can be written as a series, as an infinite sum, but this, due to Campbell-Hausdorff and the Slater-Condon rule, that this expression here, yeah, is only a fourth order polynomial in the excitation operator. Yeah? So really computable, and in our application it becomes also much simpler. And the other thing is now what kind of excitations we are interested in. Yeah, okay, and if we do all excitations, for which in the linear case we get the full ZI, yeah, we get a full coupled cluster, and if the solution is not orthogonal to the reference, yeah, then the full coupled cluster gives you already the full ZI solution. Yeah, okay, yeah, but. That's not what you do in practice, because, okay, I will talk about full ZI a little bit later, yeah, for obvious reasons. What you do in practice, you restrict yourself to a certain kind of excitations, yeah? And usually you have single excitations and double excitations, possibly triple and quadruple and so on. But the standard coupled cluster goes up to double excitations. Okay, so. Okay, and now I come to the restricted ansatz. And now I try to approximate my wave function, and now I write it in this coupled cluster framework by a sum of two excitation operators, and the first is a full coupled cluster CAS excitation. Yeah, so the CAS excitations are okay. These are IJ, yeah, IJ and AB, yeah, okay, and plus, and these excitations now are the external excitations. And now I think I come to your questions. And now the external excitations look the following. So I and J are occupied orbitals, U and V are now external orbitals. Yeah, that's double X, yeah. But there is already a set.
Recording in progress.
Oh, sorry, yeah. So there's already a second type which is mixed. So you have here, you are exciting an active orbital, together with an external orbital. Yeah? Yeah? That's already a possible excitations, and both of these kind of excitations are included here. And it's for the exterior excitations, I go up only to double. Okay? Yeah? And we see that now all these excited Slater determinants, they are orthogonal to the full ZI space generated by the CAS orbitals. Yeah, okay? Yeah? But keep in mind, that's not the only one. You have already this mixed term. Yeah? Okay, and then we can write down the ansatz for the wave function. It's an approximate ansatz. And in the external, we have only single excited and double excited. But for the cusp, we have the full coupled cluster. Yeah, okay. We never computed it. Yeah, okay. Only in principle. Yeah, and then this can be written as an external excitation operator applied to a psi-cusp function. Yeah, this is now out of the full active space. Yeah, so it's a sum of many Slater determinants. Yeah, so this looks exactly like a multi-configurational reference. This is not only one reference determinant. Yeah, and this is a unknown, or the unknown external coupled cluster operator. And indeed, it is not really a multi-reference coupled cluster. It's cheating. It's fake. Yeah, yeah. But it's a surprisingly nice ansatz. We will discuss later. And the next thing is that we can compute the energy. We can compute the energy, and the energy for the coupled cluster ansatz depends only on the excitation up to order 2. Yeah, yeah. Now that's quite nice that you can write the energy as a CAS energy. Okay.
So it is fake, but do you think this ansatz has the potential of capturing important screening effects from the external?
I will show you. I think that's a good question. How good is this ansatz? What are the deficiency and what? Yeah, I come later to this point. Yeah, and the only thing is that here we need, for the energy, we need only up to second order excitations in the CAS space as well as in the external one. Okay? Next thing is, I never compute a full coupled cluster. I've never seen this. Yeah? Yeah, but I suppose now that I can do a full CI calculation. Okay? And these S are the CI amplitudes. Okay? And from the CI amplitudes, I can compute the coupled cluster amplitudes, at least for small excitations. So it goes up to 2, yeah, and this goes up to 3. Yeah? And in practice, we use only this. Okay. So, and now just...
Is this now exact or an approximation that you keep the quadratic terms only?
So the cusp is exact on the cusp space, and the coupled cluster ansatz in the external space is only an approximation. I go only to coupled cluster double external. Yeah? Okay? Yeah, that's... Yeah. Yeah. Okay. But you know that for usually a coupled cluster single double is, roughly speaking, a golden... okay. For the ground state in weak correlation. Okay, and we can consider the unlinked formulation and the linked formulation. And usually, these formulations are equivalent in this sense that these are different nonlinear equations, but the solution is the same. But this is no longer true in our case, yeah, except if the T1 external amplitudes are 0. Yeah? Okay, if they are not 0, then you can at least give you some examples where these solutions are not the same. Okay, so in the sequel, we will assume that T1 external is 0, okay, we don't need it, but if we want to have this property, we would like to assume this. And indeed, it's well known in coupled cluster theory that if we are going away from the Hartree-Fock determinant, if we use Brückner orbitals, yeah, so we transform the basis, and the Brückner orbitals, they have the best overlap with the wave function, and for the Brückner orbitals, the T1s are 0. Yeah, okay, but it's only a technical matter. So, but usually okay. So, and the next thing is, and this was some observation we did, and it has been worked out fantastically by Fabian. Yeah, that for the energy we see that we need at most. Okay, for the energy we need at most the cusp 2 amplitude, or the coupled cluster amplitudes, or vice versa, the CI amplitude. So we have only to go to order 2. Now that was already an observation which we did. But already for this, for the nonlinear, yeah, not all higher excitation amplitudes are entering the coupled cluster equation, the external one. Yeah. And if you look a little bit carefully, you can see that you can truncate this exponential, this series after T3. Only the triple excitations are entering these equations. Yeah? And it was supposed by Bartley to drop this term. Yeah? Because they are entering only with respect to the here, if here we have this mixed excitation here, where you have one excited to active and the other excited to the externals. Yeah? And then you see, okay, we're using Slater-Condon rules. Yeah? So that's an important excitation. Yeah? And what the people then do is if they have an approximate method for full ZI, yeah, or we do, or that's whatever, we compute the first 3, at least only the first 2 CI amplitudes, compute from the ZI amplitudes the coupled cluster amplitudes, and then run a standard coupled cluster double approach, where these cusp amplitudes are fixed, are given. Yeah? So it's only a subsystem of the original coupled cluster one. Yeah? Yeah? Extremely simple. Yeah? It's okay. Yeah? And okay, that's yeah, okay. And practically they have not considered the triples one, but here it's not hard to include them. Yeah? Okay.
I have one question. Are these amplitudes all uniquely defined? Because when you are the amplitudes all uniquely defined? Because when you act from external space right onto this linear combination of the terminal, there can be an amplitude.
I come to this. Yeah. Okay. So we go only this way. We have the CAS solution. Yeah. We have the full CI solution or approximate full CI solution, and we want to from this we want to compute the external. Yeah. Yeah. So this is given. Yeah. This is given, and this should be computed. Yeah. Okay. That's. And here in this framework, and it's already we see already the following thing. It is a remarkable observation, which I did not during that time, but this Simon has shown me that now we have the following. Now the cusp, yeah, the cusp function is a right eigenvector of this non-symmetric Hamiltonian, transformed Hamiltonian. Yeah. Okay. Yeah? And it is compared to the large space with the large basis. Yeah? It is living in a relatively small space. Okay, yeah. So that's yeah. Okay. And this is and if we use a normalization, so that's the right eigenvector. Okay. And now what's the problem about this? Yeah? Nice method and how good it is. The problem is that even the cusp space, yeah, can be very large. Yeah? So formally, what the people are doing, they are in multi-reference, they are using only very few active orbitals, and they have to compute the full ZI solution. Okay, that's yeah. Okay, and now we are going the other way around. We say, okay, so here we have a relatively small full ZI space, but not small, not large. Yeah? And we want to use we want to apply an approximate full ZI approach. Yeah? I think one of you, Noyan, has said full ZI is a good method. Yeah, yeah. Okay, it's okay. And as an approximate full ZI, an approximation of full ZI, we would like to consider what is called tensor network states. And now how I come from this picture with its excitation amplitudes to the picture of tensors. And even you see that we have to incorporate the antisymmetry. And the point is very simple. Yeah? Because now we are coding our Slater determinants by an occupation number labeling. Yeah? So one on the third position means that the third orbital, the third basis function, is included in the determinant. A 0 means it is not included. Okay? These are qubits. So more or less you transform it into a qubit picture. Yeah? Okay. Yeah? And then you obtain much more possible combination of Slater determinants. So Slater determinants we are interested in are exactly those which have exactly capital N ones. But we forget it at a moment. Yeah? Okay. And so the space where we are working in with this parametrization is in wave function is a Fock space. Now, since we have an expansion, every member of the Fock space is a linear combination of Slater determinants, and then we have encoded this index in this form. Then this is a number depending on these indices. Okay, and that's exactly a tensor. It depends on d indices, where each index only moves from 0 to 1. Okay, yeah. And okay, the next thing is, it's also very clear, okay, I go a little bit further. And the next thing is that now we are in the discrete space. So this is completely discrete. And the discrete formulation, so this tensor here, or this vector, or what you ever see that's in this space, yeah, corresponds to a full ZI wave function. Okay, and now we are introducing the following operators, and they are not basis dependent because the representation is basis dependent. This is this one, this one, this one, and that's just the identity. And then I consider the Schrdinger product of these operators. And these operators play exactly the role of the annihilation and creation operator. So we just can really rewrite the second quantization formulations in these linear algebra terms. Okay? Yeah? The problem is that the dimension of this space is extremely large, even larger than our full ZI space. Yeah. And how we get rid of this problem? Now we are interested in a submanifold of all possible tensors. Yeah? And this submanifold, yeah, so you see that here this is given these indices, this is a real number. And this can be written as a matrix depending on the first index, another matrix depending on the second, and so on. And these matrix sizes are such that matrix multiplication is well defined. So it's just written as a multiple sum over these products. Yeah? Never do the summation, but what you observe here is that you see what is the dimension of this space? It is 2 to the power d. But now, what is the size of these matrices, of these terms here? Yeah, it is a tensor having only 3 kind of indices. Here it's going from 0 and 1, but here it's going from 1 to an upper limit. In mathematics, we call it rank because it comes from a matrix decomposition. In physics, they call it bond dimensions. Okay? Yeah? And then you see that this here, this representation is data sparse. So formally, you have only this number. So D is this number here. It is linear in D, and it is quadratical here in the maximum of all these bond dimensions or ranks. Okay. Yeah? So it no longer scales exponentially with D, only linearly here. Yeah? The only thing is that this bond dimension can be quite large. Yeah? If you make it sufficiently large, you can recover any tensor, but then you are already in this full space. Okay? And what is very nice in this respect is, so just you put one point here, and now put all indices from the left casted in one index, and from the right in the other index. And then you see that this is something like you have a decomposition in a product of vectors with these indices plus this one. So that's a type of Schmidt decomposition. Yeah, okay? And these indices, they should be defined that all these Schmidt decompositions in between have exactly the rank which is a bond dimension. Yeah? So that's now really it's quite a trick to use Schmidt decomposition or singular value decomposition to work with tensors. It's a very nice parameterization, and it has been known. I think it has been known that Steve White introduced the DMRG, but he didn't know this. It was two, I think, Swedish guys and so on. They observed it a little bit later, and. But the full thing have been understood in the sense of matrix product states here, I would say in 2004 by the Vidal decomposition, by this community, Fastrada and so on. In mathematics, we have not been aware about this. And it has been redeveloped by Ivan Ozeledets in 2009, and he called it tensor trains. Yeah? And Hackbusch has a more general development, which in physics you will call it tree tensor networks, and okay, yeah. And now the thing is, the problem is here. The problem is now how to compute eigenvalues of this operator. You see that the operator here is tractable, yeah. Yeah. So these matrices are in this large space, but it's just the sum of rank 1 terms. Okay. It is not a small sum, but it is tractable, it is a sum. So you can apply an operator to a tensor, you can compute inner products, and what you do is you just do a minimization here of the energy, and in this minimization you make the following, practically or simplified, you keep all components fixed, yeah, except one. And then you obtain a linear space, and then you optimize this component. And afterwards, you have a post-processing, which means an orthogonalization, and then you go to the next component. This is not DMRG. This is single-site DMRG. Yeah? I have called it ALS because it's come from different point of view. Yeah? But at least I will say there are some method. There are some methods really computing, solving is a eigenvalue problem or even linear equations with this type of ansatz. Another possibility is it can show that this is a manifold and you use Riemannian gradients and Riemannian approximations. Yeah? That's not often used in physics, but that's possible too. Okay. So, and now when I saw this I thought, oh, paf, that's a method to treat Schrdinger equation. There's only the problem is that you need in quantum chemistry you need extremely high accuracies, yeah, and this requires that you need large ranks or large bond dimensions, yeah, and really if you go to practical problems they are really large, much larger than we mathematicians would consider. So the convergence, these methods are converging. Physics are telling you the quantum chemistry that doesn't make sense, but no, they are converging, but they are converging slowly. And in particular, the coupled cluster, also single the CI double solution, yeah, converges, if you put it in this framework, converges slowly. Yeah? Yeah? So practically, what we can solve here, we can solve these systems up to only a moderate number of basis functions. I would say 50 spatial, which means 100, is still a dream. Yeah? Yeah? Okay. Yeah, but it's at least d equal between 50 and 100 is possible. But this means that now here d, the dimensionality, is the size of the basis. That your basis set error can be, it becomes quite large. Yeah, okay. And what we are interested from this perspective here is that we want to do this calculation, but in order to get rid of the basis set error or part of the basis set error, we want to have some additional correction term. Okay. And for this additional correction term, this method comes into play, okay? And here are some 2 papers of us, and in particular in this paper, they have shown that this ansatz, they applied this ansatz for the dissociation of diatomic molecules. Typical ones, nitrogen 2, chromium 2, and so on. Yeah? And it turns out that this type of they call it tailored Taylor-coupled cluster ansatz. This has almost the accuracy of coupled cluster, single, double, triple, quadruple. Yeah? It was extremely, or at least here, it was extremely accurate. Yeah? And even it was much more accurate than they can do only with DMRG. Yeah, okay. And then we started, our analysis, and in my slides is a chapter about mathematical analysis. I will skip it. I have never seen here a talk about mathematical analysis. Yeah, but I want to show you they have already done some numerical experiments. And these are relatively small experiments, so we considered k is equal to 28, yeah? Spatial orbital, so twice the number. But it is not really large for coupled cluster. It's relatively small. But for this number, we can already compute a highly precise DMRG solution. And so we are really able to compute reference solution. Yeah? Which are very close to the full CI. I would say almost exactly. And here in the equilibrium distance, we use for the reference, we use single, coupled cluster single, double, triple, and quadruple. And even go a little bit further. Yeah? It's the Heinz Gauss, and so they have really developed these kind of codes, and if you say coupled cluster is slow, this is a mess. Yeah, but if you are really brave, you can do it, and that's for computing the reference, and then we choose now the number of orbitals inside our active space. Yeah, okay. But on the other hand, if we use here 15 spatial orbitals, then only 13 are left for the coupled cluster. Yeah, okay, so it's not a really good numerical study, but it shows something interestingly. And it turns really out that at first you see, so if you here that's a truncation parameter for DMRG, it's not the one dimension. Yeah, so if you work too sloppy, yeah, that's the wrong one. So if you work not accurately here, and then you see everything works fine, and now it just breaks down. Yeah? And then even if we go further, if we have here if we go to this, and then we have almost the full ZI space, yeah? Even we see this artifact, and here you see that's strange. Yeah? And so far, I would not say that we have an explanation, but something you do not want to see. If you go away from the equilibrium distance here, then it becomes a little bit better. And here you see it becomes better. So it becomes better in the case where coupled cluster is not so good. Yeah? Because you see here in this picture is a competition between DMRG and coupled cluster. Yeah? Okay, and now I come to the conclusions. So tailored coupled cluster is more like a perturbation approach or perturbative approach, only a way improving the DMRG solution. Yeah? We have an analysis, I will not talk about this. Okay, what is important here in our analysis, we see that the stability, the coupled cluster system becomes nicer, much nicer. Yeah? Okay. And the computational cost is more or less fantastic. Formally, it's more or less majorized by the coupled cluster single double formally, but practically the DMRG is. So we get a solution up to the cost of coupled cluster. So if K is large, so if you have a really large basis set, then the cost is dominated by the coupled cluster. But the whole thing already requires that your CAS space should be sufficiently large. So here you see here the equilibriums, and we are interested, what is here the optimal value here? So, okay. So, but we are not really fearing the size of the CAS space up to a certain point. That's in contrast to former a multi-reference coupled cluster. And now I think that is already what the experts I want to mention. We don't have a feedback from our coupled cluster solution to the CAS solution. Okay? So it is just one improvement, an additional thing, and no feedback. And it is not clear how to really to have variational formulations, how to compute expectation values, how to formulate excited states, how to formulate time-dependent problems, and so on. So this, and when we have observed that in the interaction from CAS to coupled cluster is fairly simple, but we do not know how to go back. For that time, and I gave up, and now recently, I think there is some remedy, but it is not implemented yet. And the idea comes from a CAS coupled cluster method, already introduced by Adamovich, Ivanov, Pietzuch, and so on. And it's a well-established method. Often they do not CASP, they only they use CI up to fourth order excitations. But here we can use this approach and combine it by what Siemens quite likes. It's a bivariational formulation. It's a variational formulation introduced by Apponen. And so that's a topic. That's a baby here of Siemens. And now we look what's coming out. Okay, so let us consider the external coupled cluster equations. And then we see, I already have seen that the energy, so the thought energy, is an eigenfunction of this similarity transform in Hamiltonian projected to the CAS space. Okay? The only thing is how to compute it. Look later. And now it is the right eigenvalue because this is a non-symmetric operator. And indeed, what we want to do further is we do not use the full ZI CAS space. We use a low-dimensional manifold given by matrix product states. Okay. And now we formulate, that's a bivariational formulation. And now we formulate the problem in the following way, that we want to optimize. It is a saddle point. It's not minimization nor optimization. But we introduce the following functional, which is a Rolik type functional. In the symmetric case, in the Hermitian case, psi tilde is equal to psi. But now we introduce two independent functions, psi tilde and psi, and normalize it by the interaction of this. So So this is a little bit bi-orthogonal framework. Okay. And now we want to optimize this expression depending on psi tilde and psi. And additionally, what we have to keep in mind is that our operator here depends on the coupled cluster amplitudes. And they are not known a priori. So we want to optimize it with respect to a constraint condition. And the constraint condition is the linked amplitude equations, okay? Yeah? And in order to do this optimization, we introduce a Lagrangian, which is just this Rayleigh quotient here, plus a Lagrange multiplier times the linked amplitude equations. It is more or less the Helgaker ansatz for doing variational Monte Carlo. Yeah? That's okay. And what we obtain here are two equations. If we differentiate with respect to psi tilde, so yeah, then we get an eigenvalue a problem for the right eigenvalue psi cusp. Yeah? If we test this again, all possible psi tilde in psi cusp. Okay, for the full cusp first. And additionally, we get the amplitude equations. And these equations are now coupled. Yeah, so this depends also on this, and this depends on this. Okay? But we can go further. We can solve this in a self-consistent way by alternating between this equation and this equation. And what we have done so far is, in the tailored coupled cluster, we solve this where t is equal 0, and then we solve this and we stopped. Yeah? But if we have done both, then we can feed it here, and then we can continue. And I think 1 or 2 iterations are completely sufficient. Now we have but if we go to manifolds, yeah, that's due to Zeeman. If we now go to manifolds, then we have 2 possibilities. You see, this is a non-symmetric operator, non-Hermitian operator. Yeah? So we have this, the Galerkin idea is that we are projecting here to the tangent space at the right, at phi cusp, at the here, that's here. Yeah? At this to the tangent space. And if we differentiate, that must be without tilde, that's a typo. Oh, no, here, we are this one, yeah. So but the other way is, usually it is more natural that the variation is on the tangent space of the dual function psi tilde. Yeah? Both approaches are possible. Yeah? And it is not clear what is better. Yeah? So Zeeman favors here, but Zeeman already has an analysis where we have which includes this flip gradient, and that supports this scheme. Yeah? I think in Garnet-Chan has already a paper about non-symmetric Hamiltonians or non-Hermitian Hamiltonians, and I think he used this one. When we do DMRG for non-symmetric operators, we usually use this one. Yeah? So that's a new idea. That's a new idea. And instead of the tangent space, we can already do what we do in DMRG, at least in single-site DMRG or ALS. So we are thinking about developing now a bivariational DMRG, yeah? In contrast to this. Yeah? But it's not clear which. Okay. And now I come. Yeah.
What is T tilde? Because I thought
what
it hasn't been defined.
What is the tangent space?
What is phi tilde?
The tilde, you see, we have 2 functions. Yeah? Yeah? Usually, phi here is, or psi is the right eigenfunction, and psi tilde is the left eigenfunction. But that's only true for linear operators. And here in this Lagrangian, we see, you will see later, that that's the equation for the dual function here is not an eigenvalue problem. You have this inhomogeneity. But you have solved the right eigenvalue problem, you know the energy, and you can solve this system too. Yeah? Okay, and in order to do really time-dependent calculations and computing expectation values, we do need the dual solution, and additionally, we need the Lagrange multiplier. Yeah, that's more or less it's the same, not exactly what Helgak are doing is in this linear response theory. Yeah? Yeah? So the important problem is that here we include this, yeah? And this can be more or less derived in this. Yeah. So now we come to what is the form of these matrices here. Yeah? And maybe this is just computation. I consider now only the double ones here, a couple cluster double. And the first one is, this is a working equation on the CAS space. Yeah? This is this Nonamicing operator. And this usually this is used by using Baker-Campbell-Hausdorff formula, fourth order polynomial, too complicated. It turns out that if you apply this operator, yeah, to the left part, yeah, then you have to apply the adjoint, which is the de-excitation operator. Yeah? And the de-excitation operator applied to most excited is zero, not to all. Yeah? But in this case, and then we obtain that this is just given by this operator. So it's an original Hamiltonian restricted to the CAS space plus a product of the Hamiltonian times the second order, and even the second order external amplitudes here. And if you and now how to do this computation? And now it's easy. So if you look to our DMRG and to our formulation, we can write this in second quantization. It's quite easy, and it turns up that H times T2 is something like a 3-particle operator. Yeah, and it is really computable because D is much smaller. Yeah, so it's scaling with D to the power 6, but this can be smaller than K. So it should be smaller here. Yeah, sorry. Yeah, okay. Yeah. And the other thing is what I really fascinating here is this has the same structure formally, a little bit similar structure like the explicit correlated method introduced by Handy and Boyce. Yeah. Yeah. And by this approach, I think really we can do both. We can do a lot of things I will discuss. And the second equation is a little bit more complicated, but this can be treated in the same way as a Taylor-Coupled cluster. So this is an iteration scheme, self-consistent iteration scheme. You alternate between these two equations, and if you have the solution, then you can compute the dual ones. What is interesting here, we can differentiate the link coupled cluster equation with respect to the coupled cluster amplitudes. And that's necessary to compute the Lagrange multiplier. Yeah? That's already known by Helgak and Monkost and so on. Yeah? We never have to differentiate the first expression with respect to t. Yeah? That's already an important fact. Yeah? So I think in this respect, this is really not cheating. It's really a valid multi-reference coupled cluster method. Yeah? The analysis for the TCZ can be just extended to this case. And now degenerate and quasi-degenerate ground states can be computed too. The cost, if you have a large K, then the cost is almost the cost of a coupled cluster single double. Yeah? And then we can compute expectation values. We can compute excited states. I think that's a method, the coupled cluster method for computing excited states. Yeah? And what Simon already interested in, here he already has a time-dependent formulation. Yeah? So he formulates everything in this bivariational framework. Yeah? And then that's the action integral. And then he looked for the stationary points yeah, of these action integrals, and where now the psi is an unknown, so you get you get a Nonamicing Schrdinger type equation for psi. For psi tilde, you get a little bit else, and you get you get a differential equation for the amplitudes. I think that's even standard time-dependent coupled cluster in this Helgaker framework and for the Lagrange multipliers. Yeah? Okay. The only thing is, what is really, our solution is still biased by the choice of our, not of our reference determinant, by the choice of our occupied orbitals. Yeah? So the reference here is now a very good CAS solution. Yeah? Yeah, it's really multi-reference. Yeah, but the coupled cluster, the excitations, yeah, are not arbitrary excitations. Yeah? They are only these excitations here. And it is not clear that this is sufficient. Yeah? But you see, I think, so we already have observed that this external, externally correlated coupled cluster is relatively insensitive to the choice of the reference. Yeah? And you see already that you use a coupled cluster to approximate the cusp. And this is, I would say, a two-dimensional thing. And in this respect, the double excited amplitudes are almost complete. Yeah? So that's something which is not clear in advance, but I'm very hopeful. Yeah? Yeah? And though we should have a method at the end, yeah, based on a DMRG a little bit larger. On the cusp space, we have DMRG for 3 particle operators, but that's like explicitly correlated. We have explicit correlation, weak correlation, obtained from the coupled cluster. Yeah, yeah, yeah. Well, we have it here. Okay. That's okay. And I think here next chapter is about theoretical analysis. I do not know what time it, but I'm a little bit exhausted, and I think that's the point I would like to stop. It's okay, or?
Yes, absolutely.
Okay.